My name is Jessica Webster and this is my Lab 9. In this lab we observe a spring mass system's two-dimensional movement while oscillating on a spring. The lab's main result is that the change in the kinetic energy plus the change in the potential energy equals 0, and that the periods for y and x values are independent from one another. The first step in this lab was to analyze the mass spring system using tracker. I calibrated this using the spring's equilibrium length 0.7 meters. The mass was 0.402 kilograms, and the video had a frame rate of 10.5 frames per second. The time interval began once there was no longer a contact force to 9.49 seconds. I saved this position data to a CSV file that will be used in our computational model. Here you will see some physics principles at work in this lab. The momentum principle is used in the position and velocity update equations. The energy principle is used in finding the system's kinetic energy, gravitational potential energy, and spring potential energy. On a more basic note, Hooke's law is used to define spring properties such as its stiffness. I initialized the code from Lab 8 using the given mass and the initial position from tracker. Then I read in my observed data points, which will allow me to compare my observed and predicted values. Then I found the spring stiffness and L naught using Hooke's law. Now for the predicted data's while loop. Right before this, I initialized both the kinetic and potential spring energy. I also highlighted the code that uses the momentum and energy principles to update the system's position and track its energy respectively. In this next loop, I read in my observed data points to plot my observed movement. This graph line of code allows me to directly compare my observed and predicted data points against time. Now I run my code. You'll see the predicted movement by the orange ball and the observed movement by the blue ball. They are not exactly the same, but this is probably because of technical error in my tracker analysis. To the left, you'll see a graph of time versus the predicted and observed y position values. To find the period of oscillation, I subtracted the time from one crest to the previous one. The predicted and observed period times are slightly off, but still very close. I did the same analysis on this graph representing time versus the predicted and observed x values. The difference in period times, again, probably has to do with minor technical errors. Also, please take note that this period time for the x values is a little bit bigger than period time for the y values. And for the last of my graph analyses, I have the different energy values for my predicted spring mass energy system. In red, I have the total energy. In green, the change in kinetic energy, and in blue, the change in spring potential energy, which I've defined using 1/2 ks squared. Note that you can visually see how the change in kinetic energy plus the change in potential energy equals the change in energy total. For the first what does it mean question, the periods for the y and x values do differ, because they are independent from one another. The system acting as a pendulum means the system having a greater x displacement than y, which accounts for the x position values having a greater period than the y values. With our system of the mass, spring, and earth, there are no substantial surrounding forces affecting the system with work, and there are no transfers between the system and surroundings, aka Q. However, there are changes to the system which are accounted for with the potential spring force acting within the system, as well as the gravitational potential force. Therefore, the energy principle is satisfied. Lastly, by changing the origin from y equals 0 to y equals L naught plus mg over s, or in this case, negative 0.7 in the y direction, the physics of the system does not change. The potential energy doesn't change because it's dependent upon the displacement, not upon specific points. The kinetic energy doesn't change because it's simply a property of the system and doesn't depend on distance. Therefore, the plots would look exactly the same. Thank you so much.